Okay, so you made it through all 2.5 hours of oxygenation, circulation, and a little 13-minute Maslow's video. Now it's time for a break, a math break. We'll do a little bit of dosage calc and keep things going. We'll start with a little scenario. The nurse is caring for a client with pneumonia, and among other things, the client is to receive oral antibiotic therapy. The order that you have is amoxicillin 500 milligrams PO, Q8 hours, and the label is how it comes supplied in a suspension that's 200 milligrams per 5 mLs. And we want to know how many mLs will the nurse administer per dose. So we have to set it up in dimensional analysis. Give me 1 second. So some of you might be a little bit new to dimensional analysis, and that's okay. I have a really foolproof way of setting it up. It's maybe a little different from what you learned on ATI, but not essentially. What I do is I start where I hope to finish, and then I work backwards. So if I know that my answer is going to have mLs per dose, I make sure I start with that. mLs per dose. That's my answer. And then I work backwards. I make sure all my mLs are on top, and I make sure somehow that that dose part is on the bottom, and then anything else that's in the problem, like these milligrams, are going to cancel out. And then I'll just go ahead and do the math. And as long as I do my computation correctly, I'm pretty much assured I'm going to get the right answer. So, okay, I want mLs on the top. The only mLs I have in this problem is the 5 mLs that are in that supplied as, the 200 milligrams to 5 mLs. So let's start there. We'll put 5 mLs here. 5 mLs is equivalent to a 200 milligram dose, right? Okay. Well, now I need the dose on the bottom, and I need to cancel out milligrams. So up top I have the order is 1 dose equals 500 milligrams. Okay, so let's go ahead and put our 500 milligrams here, because that's going to cancel, and the dose here, and the dose is going to stay the same on the bottom. Now, when I mean cancel, if it's on the top and on the bottom, it kind of cancels itself out. So now when I look at it, I have mLs per dose, and I don't have any other units, so I can go ahead and multiply across, because everything that needs to be there is there, and everything that needs to be canceled is canceled. So I go ahead and multiply across, and I end up with 2,500 mLs over 200 doses, which is a ridiculous amount of medicine. We're never going to give 200 doses of something all at once, so now we have to divide the top by the bottom. So we get our calculators out if we have to do that. If not, we do the math the old-fashioned way. If you want to get real fancy, you can reduce a fraction. Some of you might not be familiar with that, so go ahead and just use your calculators and divide 2,500 by 200. You're going to end up with 12.5, make sure your decimal point is clear, mLs in your dose. Okay, and that is a realistic amount of medication. Remember that when we give you a dosage calc problem, we're never going to ask you to give 30 tablets. We're never going to ask you to give 200 mLs of something that comes essentially labeled for a teaspoon. That's just not going to happen. Remember, people with no medical knowledge at all will take 30 tablets of anything, even Tylenol, to kill themselves. So certainly we're not going to ask you to take that step away from common sense. So when you look at your answer, 12.5 is a realistic amount of medication. That's about 2.5 teaspoons. That looks about right to me. As long as you have your decimal point in the right place and you've done your computation correctly, you're going to end up with the right answer, because you set your problem up so that you had mLs per dose and you canceled out anything that didn't belong. Okay, let's try that again. So now we have a different scenario. Now the nurse is caring for a client who has a cardiac arrhythmia, and the provider writes an order. Verapamil, which is calcium channel blocker, you don't need to know that just yet, but you'll find it again. 4 milligrams IV push stat. It's supplied, I typed that in wrong, sorry, I'll fix that for you. Supplied in a vial labeled as verapamil hydrochloride injection USP, 5 milligrams to 2 mLs. And then in parentheses it says 2.5 milligrams per ml, so just pick one and stick with it. Okay, I'm going to stick with the 5 milligrams per 2 ml because it's a bigger font. And why don't I rewrite that? Okay, so there it is, a little bit simpler. The order is for 4 milligrams for a dose. It's supplied as 5 milligrams to 2 mLs solution, and I want to know how many milliliters I'm going to give in this dose that I have just been ordered to give. So, like I said, with dimensional analysis, very easy. I want to know how many mLs per dose, so let's start with that again. Remember, we want our mLs on the top and our dose on the bottom. We can start with our order, 4 milligrams per dose. Now our dose is on the bottom, and we want our mLs on the top. So 2 mLs is equivalent to 5 milligrams, and that means our milligrams are going to cancel, and that means I set it up right. So milligrams cancel. Now I can just multiply across, because I have mLs per dose. mLs per dose. I know I'm set up to do it, and as long as my math calculation's right, I'm going to be okay. So I end up with 8 mLs to 5 doses. And when I simplify that, let me get rid of some of this stuff. There I have it. 8 mLs over 5 doses equals 1.6 mLs per dose. And that is a realistic amount. And so I'm happy with that number, because I know I set my problem up right in dimensional analysis, and I know that my computation is correct. You, of course, can check that with a calculator if you can't divide 8 by 5 in your head or on paper, but 1.6 is your answer. We can try it one more time if you want. So here it is, last one for now, I promise. Our scenario now has changed. Now the nurse is caring for a client who has developed a deep vein thrombosis, otherwise known as a DVT, something we talked about as a condition that affects circulation. The nurse follows a weight-based protocol for heparin. Don't worry too much about that. You'll see it next semester. Anyway, the nurse arrives at the following dose of that medication. She wants 4,000 units IV push, stat times 1. So she wants a 4,000 unit dose. And that heparin is supplied in a vial that looks like this. Take a look at it. 5,000 units per ml. Okay? Alright, so let's kind of rewrite that. Give me a sec. So there's our problem restated in a little bit simpler of a format. We need heparin 4,000 units for our one-time dose. It comes supplied as 5,000 units in a 1 ml vial. We need to know how many ml to draw up into that syringe. So let's follow all the good principles of dimensional analysis. We want mLs per dose. We're given 1 dose. Start there, start where we hope to finish, and then we move backwards. We want our mLs on the top and our dose on the bottom. Well, let's go ahead and start at the top. 4,000 units equals 1 dose. Always write out the word units, by the way, because that U, see how sloppy my finger is on this screen? It can look like another 0, and then you've got 40,000 units, which is a tragedy. So 4,000 units equals 1 dose, okay? We've got our dose on the bottom. Now we need our mLs on the top. So we know that 1 ml is equivalent to 5,000 units, and oh, look at that, our units cancel. Well, let's go ahead, units cancel each other out. Now we're left with mLs per dose, which is the same thing we have over here, and we know we set up our problem correctly. So what do we end up with? Let me get rid of this sloppy mess here. What we end up with is 4,000. This is pretty simple. 4,000, whoops. Make that a little bit bigger. And we'll put that over 5,000. And that gives us our mLs per dose. Oops, sorry, let me write that out. Right? Okay, so all we have to do is divide the top by the bottom, and we end up with 0.8 mLs. That's what we're going to draw up in our syringe to get a 4,000 unit dose, and that does make sense. 4,000 is less than 5,000. 5,000 is an ml, so yeah, a little less than an ml is about right. 0.8 is a realistic dose, and we know we set it up right because we followed all the rules of dimensional analysis, and now we have our answer 0.8. It really wasn't that painful.